Swayam Prabha. Digital India. Educated India.
Good morning. This is the third lecture on similarity analysis. The contents of the lecture are similarity rule for compressible flow, isentropic efficiency, then I'll discuss on characteristics map of multi-stage compression, characteristics map of multi-stage turbine, then I'll discuss on specific speed for compressible flow. Let us consider the compressible flow, that is turbomachines handling compressible flow. Here the performance parameter, which are del H0s, that is isentropic enthalpy rise or drop, efficiency, and the power, eta and P, of a turbomachines handling compressible flow can be expressed functionally as del H0 S, eta and P is a function of mu, omega, d, m dot, rho 01, a01, and gamma. When mu is the viscosity, omega is the rotational speed in radian per second, d is the diameter of the impeller, m dot mass flow rate through the machine, rho 01 is the stagnation density at the entry of the machine. Similarly, A01 is the stagnation speed of sound at the entry of the machines, and gamma is equal to Cp by Cv. Del H0s is the stagnation change of enthalpy across the machine. For a compression, it will be stagnation enthalpy rise. For a turbine, it will be stagnation enthalpy drop. Now, if we carry out the dimensional analysis, so now this enthalpy, eta and P can be expressed as some non-dimensional group such as del H0 S divided by omega square by d square, which represents the xi, eta, and the power coefficient, which is equal to P divided by rho 01's omega cube and d to the power 5, can be expressed as a function of m dot divided by rho 0 omega d to the power cube, that is non-dimensional mass flow rate through the machines. Now rho 01 omega d squared by mu, this is some sorts of Reynolds number, and omega d by A01 is the blade Mach number, and gamma is the ratio of Cp by Cv. Now look, omega multiplied by d represents the blade speed. So omega d by A01 will represent the blade Mach number. Similarly, omega d is the blade speed proportional to blade speed u. So rho 0 1 u d by mu is the form of Reynolds number. So the first term here, that is non-national mass flow rate, is called the capacity of the machines. So non-national enthalpy rise, which is xi, efficiency, and the power coefficient for a compressible machine is a function of capacity, Reynolds number, blade Mach number, and gamma. Gamma is ratio of Cp by Cv. Now what is the functional relationship that I have established earlier? I would like to simplify further. With respect to that, I'll write the expression of isotopic enthalpy rise or drop across the machine can be given by del A0 is equal to Cp into T02S minus T01, where T02S is the stagnation temperature at the exit of the turbo machines. Now the ratio of T02S by T01 can be expressed as ratio of P02 by P01. So T02S by T01 to the power equal to P02 by P01 to the power gamma minus 1 by gamma. Further, if we consider the ideal gas relation, then Cp is equal to gamma R by gamma minus 1, and A01 squared is equal to gamma R into T01. Thus, combine these two relations, I can express as A01 squared is equal to gamma minus 1 into Cp into T01. Thus, we can express the ratio of A0S and A01 square as, so A0S divided by A01 square equal to del A0S divided by gamma minus 1 into Cp into T01. Put here from here the value of A01. Now combine this relation and the expression of del A0S given here. If you combine these two, you can express as del A0S by A01 square is nothing but the function of P02 by P01 and gamma. Please follow this expression. And then here I can conclude that del A0S by A01 square is a function of P02 by P01 and gamma. We have already indicated that del A0S divided by A01 square can be expressed as a function of P02 by P01, which is the pressure ratio of the machines. Again, omega d divided by A01 can be expressed as m, where m being the blade Mach number, as omega d proportional to the blade speed. Thus, from this relation of blade Mach number, I can say omega d proportional to A01, and hence del A0S by omega squared d squared, which is stagnation enthalpy rise coefficient, can be represented as xi is proportional to del A0s by A01 square, and thus is also a function of P02 by P01. So what I have shown here that enthalpy rise coefficient can be expressed as a function of pressure ratio. Now using the equation of state P by rho is equal to RT, the non-dimensional mass flow can be expressed as m tilde is equal to m dot divided by rho 01 A01 into d square. Now let's put the value of A01 and rho 01, then it will be m dot r into T01 divided by P01 root over gamma r T01 into d square. Now let's simplify further. Then it will become that m dot root over gamma r T01 divided by d square P01 into gamma. So this is non-dimensional mass flow rate m tilde, and it's referred as flow capacity. So flow capacity of the machine is m tilde. Similarly, the power coefficient can be expressed as P tilde as P divided by rho 01 A01 to the power cube into d square. Now P can be expressed as m dot Cp into delta 0. Delta 0 is the temperature rise across the machine. Now I can club this into two groups. So in the denominator I can write this is rho 01 A01 d square into A01 square. Now you can understand this is including m dot, and this bracketed quantity is nothing but m tilde. So this will become m tilde into Cp delta 0 by A01 square. Put the value of A01. Now then it will become m tilde divided by gamma minus 1 del T0 by T01. So what the conclusion? Conclusion is power coefficient can be expressed as del T0 by T01. So similarly, the enthalpy rise, non-dimensional enthalpy rise, can be expressed as a function of pressure ratio that I have shown in the earlier page. So thus, I can express now the functional relationship that I have established earlier can be simplified, and it can be in more useful form as that enthalpy, non-dimensional enthalpy rise can be expressed also, represented also as pressure ratio, enthalpy, and this is also as that is power coefficient can be expressed also del T0 by T01. So I can write P02 by P01 eta and del T0 by T01. One express, one represents the enthalpy rise across the machine, and the other one represent the pressure coefficients. So P02 by P01 eta and del T0 by T01 can be expressed as a function of capacity, flow capacity, Mach number, Reynolds number, and gamma. Now for machines of a given size handling a single gas, gamma R D can be omitted from the above expressions that I have derived earlier. If in addition the machine operates at a high Reynolds number, then the effect of Reynolds number can also be dropped. Thus, the above expression which has been derived earlier can be written as P02 by P01 eta del T0 by T01 is a function of m dot root over T01 by P01 and omega divided by root over T01. Now m dot root over T01 by P01 represents the flow capacity and omega by root over T01 represents the speed of the machines. So this is a simplified relations for a particular machine. Now from this relation, I can now establish how the pressure rise or the temperature rise will change with mass flow rate and speed of the machine. Now let us define the isentropic efficiency of a turbine or compressors. Now here I have indicated the TS diagram and I have shown you a turbine, indeed a handling compressible flow. So 1, 2 is the actual temperature drop and 1, 2 dash is the isentropic temperature drop. For a turbine, isentropic temperature drop will be higher than the actual temperature drop. Now P01 is the pressure at inlet and P02 is the pressure at exit, obviously total pressure. So eta T efficiency, isentropic efficiency for a turbine can be expressed as del T del A0 divided by del A0S, actual enthalpy change divided by isentropic enthalpy change, which can be expressed as a ratio of del T0 by T01 divided by P01 by P02 to the power gamma minus 1 by gamma minus 1. Similarly, isentropic efficiency for a compression can be expressed as del A0S by A0. Here actual rise, temperature rise or enthalpy rise for a compression will be higher than the isentropic. And this can be expressed now as P02 divided by P01 to the power gamma by gamma minus 1 divided by del T0 by T01, where del T0 represents the temperature rise or temperature drop across the machine. I would now discuss the characteristics map of a multi-stage compressor. Here the performance map has been presented graphically, which was represented in functional form earlier. That's why here P02 by P01 is expressed as a function of m dot root over T01 by P01, which is the flow capacity for different speed, that is omega by root over T01. So this is the performance for different speed. Now, here the isocontours of efficiency line has also been superimposed. Look, this point represents the maximum efficiency, that is, for this combination of pressure and mass flow rate the machine has been designed. Furthermore, each characteristics line has merged to the search line, which is the line of instability. Note here that for a certain speed, if we throttle the engine, its pressure will rise, efficiency will increase. At some point which is near to the search line, efficiency would become maximum, and then we'll further throttle the compressor. The pressure will increase, each blade will start stalling, and then the machine will lead to the search. So at any condition, one should not go beyond the search line, then the total operation would be unstable. This is so far about the characteristics map for a multi-stage compressor. Further, another point that must be stated here, at low pressure and high mass flow rate, this characteristics curve becomes vertical. That means if you change the pressure, no increase of mass flow rate is possible. At this condition, the Mach number across a section of the machine becomes unity and the flow is called choked. Furthermore, here a discussion regarding stall and surge appears necessary, which will be made later. Now I'll present the characteristics map of a multi-stage axial flow turbine. Here the characteristics map is represented graphically, where P01 by P02 is expressed as a function of m dot root over T01 by P01 for different operational speeds. Look here, the characteristics map of a turbine is completely different from that of a compressor, where we have seen a strong dependence of speed. However, here a weak influence of speed on characteristics has been observed for turbine. Furthermore, at any operational speed after a certain mass flow rate, the characteristics curve becomes vertical. That means after a certain mass flow rate, if you change the pressure ratio, the mass flow rate cannot be enhanced, indicating that the flow has been choked. Here I'll define the specific speed of turbo machines handling compressible flow. Now please note the isentropic work done per unit mass is given by Cp into delta 0 Is, where delta 0 Is is temperature rise or drop across the machines. Similarly, isentropic work done per unit weight can be given by Cp into delta 0 Is divided by G, which can be treated as head. So if you remember the specific speed expression for specific speed, now the specific speed for compressible flow can be expressed as Ns equal to omega root over q divided by G into del H Is to the power 3 by 4. That becomes omega into root over q divided by Cp into delta 0 Is to the power 3 by 4, where Cp is in joules per kg per K. I'll illustrate here the coordinate diagram. Before presenting coordinate diagram, I have presented here efficiency versus specific speed. This had been presented earlier. However, you know the expression of specific speed and specific diameter. However, for compressible flow, the specific diameter now is given by d into Cp delta 0 Is to the power 1/4 by root over q, and Ns can be expressed as omega root over q divided by Cb into delta 0 Is to the power 3 by 4. Now if we represent eta maximum versus specific speed, we'll realize that the radial flow machine falls in the range of specific speed 0.2 to around 0.7, 0.8, and the mixed flow in the range of 0.7 to 2.5, and 2.5 beyond is axial flow machines. And furthermore, through this graphs, through this figure, what are the message can be given that the specific speed can be used to select the different kind of machines. Rather, let me repeat, from this figure, the message can be given that the specific speed is used to select the types of compression or turbine. Different specific speed range corresponds to different kinds of machines. Now the coordinate diagram represents the specific diameter versus specific speeds. Now how this coordinate diagram has been created? In reality, we have designed large numbers of turbo machines, and thus if we select the very good design which has given almost maximum possible efficiency in that zone, then we'll realize that specific diameter of those machines and specific speed are correlated, and that correlation is given by the coordinate diagram. So thereby you will find here a lot of data points. Those are the real machines that are in existence, which has given very good efficiency. So we have superimposed some pump, compressor, fans. Few are in the radial flow impeller, few in the mixed flow zone, and few are axial flow machines. So you can realize that they are very well correlated by specific diameter and specific speed. And that line which represents the correlation, is the chordial line, which is represented here by a red line. So in any design activity, we'll first initiate the design with this chordial diagram. Here, please note that typically a centrifugal machines will have NS less than or equal to 1.5. A mixed flow machine has NS 1.5 to 2.5, while axial flow machines have NS greater than 2.5. Furthermore, according to the chordial diagram, axial flow machines in general will have high specific speed and low specific diameter, while the centrifugal machine have low specific speed and high specific diameter. Here I'll give you an example how to use the chordial diagram to initiate the design. To a designer, generally the following information will be known to him. Those information are del H.is, that is isentropic heat rise or drop across the machine, or del T0.is and Q and omega. So before initiating design, the following 3 points at least will be given to a designer, which is either del T0.is or del H0.is, Q and omega. Now from this set of information, he can assess specific speed, that's non-Neiffer's specific speed, which for a compressible flow is omega root over Q divided by Cp into del T0.is to the power 3/4. And now using the chordial diagram, from NS one can evaluate ds. So thus here I have given an example. Suppose if the calculated specific speed becomes 3.3, then the specific diameter would be 1.35 using chordial diagram, which roughly falls in the range of mixed flow machines. Now, after getting ds, one can project the diameter of the impeller would be. So d we can calculate from ds as ds root over Q divided by Cp into del T0.is to the power 1/4. Thus here we can assess about the dimension of the impeller. Furthermore, specific speed one can assess efficiency as achievable. Thus, written here, from space one can assess the kind of the impeller, whether axial or mixed flow, or and the dimension of the machine. For fixed speed would give you an idea of maximum efficiency achievable. So from this note, you can safely initiate the design process. Thank you for listening.